system last time, and in metallic system, the electrical property is not that important. The mechanical strength, all those things are important in a metallic system. So the point defects in the metallic system, probably it is not that important in our discussion. We are talking about the electrochemistry, and it's very much related to the electrical properties of the material. So metallic system is not our main concern, but for the completion of our lecture, I just quickly surveyed the pointed effects in the metal system. So you guys just take it as a reference, okay? Now, from now, we are going to talk about the non-metallic solids, pointed effects in non-metallic solids, and that is our main topic. So we are going to discuss about this chapter in details. Okay. Chapter 3, the pointed defects, in non-metallic system. much simpler than the ionic model. So we are going to discuss with this defect model from now on. We are not going to take the ionic model. But just to show you, there is a way to express this point defects in a nonmetallic system. And instead of using the defects, we prefer to use the words disorder. Okay, disorder. Basically, a disorder and defect is the same thing, but when you say defects, we have just negative feelings about this. And that is not fair, because a defect is an important thing for us to discuss. So instead of defect, I prefer to use the word disorder, but scientifically it just means the same thing. It just have a different feelings, okay? Now, the disorders in the nonmetallic system, basically, we are going to discuss about the 4 different types of disorders. Types of intrinsic disorder. One is Seung-ki disorder and Frankel disorder and anti-Frankel disorder, and then anti-structural disorder. We have 4 types of disorders. The Seung-ki disorder is vacancy of anion and cation. If we have disorder related to the vacancies of an anion and the cation at the same time, naturally we are going to have a charge balance by itself. Like Vm vacancies for cation and vacancies of anion, that is going to be charge that would have charges like this. So we are going to have this couple as a disorder. That is a Seung-ki disorder. That is going to be called Seung-ki disorder. Now, Frankel disorder is a cation, a vacancy, and interstitial. Vacancy and interstitial. Okay, so it is related to the vacancies of cation, and we're going to have interstitial of the cations. We should say it's just a displacement of the cations. That is the Frankel disorder. Okay. And anti-Frankel is the vacancies and interstitial of the anions. Okay, that is related to the anion, vacancy, and interstitial, so that we have vacancies of anion and interstitial of anions. And anti-structural disorder is the replacement of anion and cation. Anion and cation. In real practice, we've never seen this anti-structural disorder. It is very difficult to replace the anion with the cation in the one structure. But we can think of this like, in this case, it is replaced, then we have a doubly charged negative and then positive, something like this. Okay? And let me give you the examples of this. Seung-ki disorder case, alkali halides. Like NaCl and MgO, KBr, and the Frankel disorder is salt, silver, and copper bromide. And anti-Frankel, we do have examples for this, like PbF2, zirconium oxide. This is a very good, famous material for the oxygen sensor and the calcium fluoride things. And anti-structural disorder, we do not have the examples. Let me give you some examples. Okay? Non-stoichiometry. Non-stoichiometry. Like if we have a FeO, we can have Fe 1.050 or Fe 0.950, and solubility limit. And then we have a 5% Fe interstitial, doubly charged, and in this case, 5% of vacancies Fe doubly charged to maintain this stoichiometries. And this is a Frankel disorder. Now, another famous example, this is example number 1. Another famous example is going to be zirconium oxide, which is the oxygen sensor or oxygen pump. 4O2. Okay. And if you dope zirconia with calcium, oxide, you can dope this thing up to 10%. Now, 10% calcium ions excess, okay? Then calcium on zirconium side, and it's doubly negatively charged because it's 2 positive charges replace the 4 positive charges side, okay? And then we have to create the vacancies of oxygen to maintain the charge balance. And this oxygen is going to use as oxygen sensor or oxygen pump. Now, the famous example is the doping in semiconductor. Doping in semiconductor. Like if you dope the silicon with the boron is a substitutional, then the boron is on the silicon side is going to be negatively charged, and then it's going to be balanced with the holes. Okay? And if you replace the silicon with the phosphorus, phosphorus on silicon side is the positively charged, and then it is balanced with the creation of electrons. Okay? And as you can see, this doping thing also can be thought as a chemical reactions, okay, with the ionization energies. It can produce the electrons and holes as a reactant. Okay, we can approach this as a chemical reaction. That is going to be done shortly. Okay, this is a p-type. This is the n-type dopant. So let's look into the chemical reactions. And then we have a quasi-chemical chemical reaction approach to defect equilibrium. This means we are going to treat defects as chemical species. And then we use the law of mass action. We usually call the LMA, okay? So what we are saying here is that we have a chemical reactions like XBB and XCC plus XDD, okay? And we are going to see an equilibrium for the Gibbs energy of this chemical reaction is 0 for equilibrium. Okay. And chemical potential of each element should be the 0. This means the reactants and product should be balanced. The left-hand side, XL, chemical potential L, should be equal to right-hand side, XR, UR. Okay? Here the excuse me. Mu I is the chemical potential. And that is the partial molar free energy of species I. Mu I is equal to round G over round Xi, isothermal, isopressure, and that is mu I 0 RT ln activity of AI, where mu I 0 is chemical potential. In some arbitrary reference state. Well, this all we know already, right? So with this, the equation of this and this fact can be written as XA mu A naught XB mu B naught minus XC mu C naught minus XD mu D naught should be equal to RT and then activity of C XC, activity of D XD, activity of A XA, activity of B XB. Okay, and this part is nothing but minus delta G naught, which is going to be called the standard Gibbs free energy change. Per mole of the reaction. Okay, and this part now is equilibrium equilibrium constant. Equilibrium constant. K. So that means delta minus delta G naught is equal to RT ln K. Right? And K is equal to exponential minus the delta G naught over RT. And delta G is delta H minus T delta S. K now is equal to exponential delta S naught over R. And exponential minus delta H naught over RT. And this is temperature independent term. Temperature independent. So we can see that K is K naught exponential minus delta H naught over RT. And as we did in the metallic system, we neglect PV term volume change of this reaction, then now K can be said as K naught exponential minus delta U internal energy over RT. And that internal energy is related to the bonding state of the defects with the host matrix. Okay? And the equilibrium constant, K, we have something to say about the activities. Activity of A is related to the concentration Ni with the gamma, the activity coefficient. Here, the gamma is activity coefficient. This activity coefficient is just the empirical correction factor. Okay, well, that means we don't know theoretically why is that, but Raoult's law says gamma is equal to 1. Okay? In Henry's law, in the region of the Henry's law, gamma is some constant value. Okay? So, in both cases, the gamma is not a function of the concentration, we should say. So this activity related to the equilibrium constant K can be presented with some constant and the concentrations. It's directly interchangeable to the concentration. Okay? Of course, in a diluted solution. And diluted solution is the actual case that we have. Now, let me give you the typical systematic approaches for the defect equilibria. And for that, let me give you the example of elemental semiconductor. And the donor is doped. Then we want to find the defect equilibria in this case. Example of application of quasi-chemical reaction method. Okay? And then in this case, the major defects is electrons, of course, and holes, and the donors, and then ionize the donors, things like this. Okay? Then the perfect crystal is going to ionize it to have electrons and holes, and for this, the react constant is going to be electron concentration and the hole concentrations here. And the temperature dependence, Ki is equal to Ki exponential minus delta GI over KT. And the second equation we have is the ionization of the donors. That is ionization of donors. And in this case, the equilibrium constant is going to be by law of mass action indicated like this. Here, again, KD now is equal to KD naught exponential minus delta GD over KT. And we have two more equations. That is electroneutrality.